Welcome to my video on 6-2b, explicit formulas of sequences. Okay, so today we're going to continue working with sequences, but from just a slightly different perspective. So to recap what we learned in the last video, we have the following question. Given the following three sequences, which ones are arithmetic sequences? So to do this question, we have to recap the vocabulary words we learned last time. An arithmetic sequence is one that has addition or subtraction constantly from term to term. So plus 3 plus 3 plus 3, minus 4 minus 4 minus 4. The other type of sequence we learned about was called a geometric. Now, geometric sequence had times or division constantly. So times 2 times 2 times 2, divided by 5, divided by 5, divided by 5. But just remember that division is represented as a multiplication of a fraction. So divided by 5 would be represented as multiplied by 1 over 5. Now there's also the possibility that we have neither an arithmetic or geometric, and that just means the pattern may be a little more complex. Okay, it's not just adding a number or subtracting a single number or multiplying a single number or dividing a single number. There's often multiple steps that occur. Okay, so let's take a look at these three options. We have 2, 4, 6, 8, 10. That's the first one. So how do we get from 2 to 4? Well, there's two ways. You could either multiply by 2 or add 2. So you do have to look at the next term to see whether this is addition or multiplication. So to get from 4 to 6, multiplying by 2 is not going to work here. So it is going to be adding by 2. So that means the first one is going to be an arithmetic sequence. And that's because our common difference, or the number we are adding consistently, is 2. Plus 2, plus 2, plus 2. And that works for the rest of the numbers. Let's take a look at number 2. Again, we have 2 to 4, so that could either be plus or times. But to get from 4 to 8, we know that has to narrow it down to times 2. So this number 2 would be a geometric sequence. And this geometric sequence has what we call a common ratio, which is what we are multiplying by constantly, of 2. Okay, and now for the challenge. Number 3. A to A plus 2 to A plus 4 to A plus 6 to A plus 8. Well, we know to get from A to A plus 2, we are adding 2. Right? So how do we get to A plus 4? Well, we would need another adding of 2. Okay, so is A plus 4, the term before it, plus 2? And the answer is yes, right? Because 2 plus 2 is 4. So let's check it again. We would need another plus 2 to get to A plus 6. So A plus 6, is that the term before it plus 2? Yes, it is. Okay, and we can see that by adding another 2 there, we get to A plus 8. So this is actually also an arithmetic sequence with a common difference of 2 as well. Okay, so the answer for this is 1 and 3. So now that we've recapped those vocabulary words, we need to introduce another something called the explicit formula. So up until this point, we talked exclusively about recursive formulas. Now, the recursive formula, if you remember, was the building block formula. It's when you had the first term, and then what are we doing? Well, we're adding 2. So it's the term before plus 2. Term before plus 2. The explicit formula is a rule that allows you to calculate any term of the sequence. So we no longer need to build to it. So if I want to find the 50th term, I don't need to start at 1 and make my way all the way up to 50. I have an explicit formula to do that for me. So to show an example of how this works, I have a sequence 2, 4, 6, 8, 10, the one that was in the do now. And its corresponding rule, a sub n, so any term is equal to 2 times n. So how is this calculated? How do we get from here to there? Well, think about it this way. If we're looking for a sub 1, right, that means my n value is 1. So when I go to plug into my rule, I am not going to plug in a whole A1. I'm going to just plug in the subscript. Okay, we're using the subscript like a variable. And this subscript is going to be an integer because it is a term number. There's no half a term. It's always 1, 2, 3, 4. So when I get this, I get term 1 is equal to 2. So what about a sub 2? What's the second term? Well, that means I'm plugging in 2 to my rule. So 2 times 2 would give me the 4. That's where I get A2 over here equal to 4. What about my third term? So A3, A sub 3. I'm plugging in 3 to get 6. Makes sense. A4, I'm plugging in 4 to get 8. And A5, which is the last one, I'm plugging in 5 to get 10. Okay, so that's how those term numbers are calculated. Okay, so we're using the place marker as what we are substituting into our formula. So let's take a look at this. Find the first 5 terms of the sequence. Okay, so we are looking for A1, A2, A3, A4, and A5. Those are the first 5 terms. So to find A1, I'm going to plug 1 anywhere I see an n. Okay, so that's 2 times 1 is 2, minus 1 is 1. To find A2, I'm plugging in 2 wherever I see an n. 2 times 2 is 4, minus 1 is 3. For A3, I'm plugging in, 3 for n. That's 6 minus 1 is 5. A4, I'm plugging in 4 for n. That's 8 minus 1 is 7. And 5, I'm plugging in 5 for n. So we are relating the place marker with the variable that we are substituting in. Okay, so that's how these explicit formulas work. So now we need to combine the ideas of what we learned last time with what we learned this time. So there is a formula for arithmetic sequences. So this one right here is the formula you can use to find any term in an arithmetic sequence. Okay, so an is that any term. A1 is my first term, just like it was. Okay, so we're still kind of using that idea. D is still my common difference. And n is still going to be the value of my term. So what place mark am I? Okay, so let's take a look at this example to see how this works out. Write a recursive and an explicit formula for the following sequence. So when we looked at the recursive, remember, we always started with our initial term, which in this case is a minus 32. And then we always had our building steps. So an is equal to the term before it, an minus 1, plus whatever my common difference is. So how do I get from 32 to negative 20 and negative 20 to 8? Looks like I am adding 12. So that would be plus 12. Okay, so how do we write an explicit formula for this? Well, we're going to plug it into the equation above. So a sub n is equal to my first term plus my n value, which is n, since we don't have a specific place we're looking for, minus 1 times my common difference of 12. Now, this is going to be, anytime we have an arithmetic sequence, this is going to be linear. So you do want to simplify it into slope-intercept form by distributing and simplifying. So minus 32 plus 12n minus 12. And when we combine our like terms, we get 12n minus 44. Okay, so that is the explicit formula. So how would I use this? Well, let's say I wanted to find the 50th term. All I would do is plug in 50 for n. So what is 12 times 50 minus 44? And that would be 500 and, 56. Okay? So that's exactly what we're going to do in this example. If they ask you to find a particular term, in the worksheet I gave you for the last video, I had you calculating this starting at term 1 and building our way. Now, who wants to do that? Who wants to find term 2, 3, 4, 5, all the way up to 30, 31, and 32? Not me. So if I have a high number term like that, that's a hint that you're going to use your explicit formula. Okay, so typically we wouldn't know whether this is arithmetic or geometric, so we'd see how we get from term to term. So this would be plus 3, plus 3. It's consistent. Okay, that means my common difference is 3. And I'm going to plug it into this formula. A sub n is equal to a1 plus n minus 1d. Okay, well, what is my n value? My n value is the term number, so that's a sub 32. A1 is my first term, plus, and n is going to be the same as that n right there. And my common difference of 3. So now from here, I can type that directly into my calculator to get my value. And I would get, if you type this in, a sub 32 is equal to 127. So that means if I follow the pattern all the way through, I should get 127 as my 32nd term. So let's take a look at how this looks in a word problem. The problem says the number of seats in the first 16 rows in a section of an arena form an arithmetic sequence. There are 20 seats in row 1 and 23 seats in row 2. How many seats are there in row 16? Well, let's write out what we have. We have that A1 is equal to 20, and A2, right, because row 2 is equal to 23. We also know that it's arithmetic, which means it's going to be adding or subtracting. So how do we get from 20 to 23? We are adding a 3. So now if I want to find what happens in row 16, I can substitute directly into the formula. A sub n is equal to A1 n minus 1d. So my first term is 20 plus 16 minus 1 times 3. If you plug that all into your calculator, you should get A16 is equal to 65. So that means in row 16, I have 65